Hi, good morning, everyone. This is Mr. Pepin. Today's Matter and Energy, day one of your Corona break. The board is right in front of you. I'm going to go through a couple of different formula and important things that you need to know. Then we'll work through some problems that will be very familiar to you if you've already started on the packet. So, to start with, this formula right here, speed is equal to lambda times frequency, is one of the most important formulas that we will be learning in Chapter 11. We'll also apply it to Chapter 12. Notice the inverse relationship between wavelength and frequency. In other words, the longer the wavelength, the smaller the frequency. Okay? Now, right here, the relationship between period and frequency. Period and frequency are reciprocals. That means they are one over the other, as you can clearly see here. The amplitude, which is the relative height of a wave, the distance from the midpoint to either the crest or the trough, is equal to 1/2 times the wave height. The wave height is the distance between the crest and the trough. Okay, we're not really going to be using that one for this class, but I figured it was important. The speed of sound in air is equal to 331 meters per second plus 0.61 times the quantity T divided by 1 degree Celsius. Note, to use this, our temperature will have to be in degrees Celsius. If you are given a temperature in degrees Fahrenheit, use the formula given in chapter 1 or 2 of the book in order to convert to Celsius. Now, our relationship between intensity and distance. The distance is equal to the inverse square, or the intensity is equal to the inverse square of the distance, or I is equal to 1 over d squared. Now we have our harmonic formulas. So ideal harmonic frequency is equal to the fundamental frequency times the harmonic number. Okay? And the harmonic ratios on page 271 will be important for some problems in this class. Okay? Now, some important things to know. The speed of sound at 25 degrees Celsius is 346 meters per second. The speed of light in a vacuum is about 3 times 10 to the 8th meters per second. Both of these constants you will need to memorize. The bell or decibel is the unit of intensity and uses the logarithmic scale, which means an increase of 1, you multiply by that power of 10. The hertz is the unit of frequency. A hertz is also equal to a per second, or 1 divided by a second. The 7 notes in music are A, B, C, D, E, F, and G. After the 7th note, you go back to A for your 8th note. The distance between one note and its 8th interval, or space between, is called an octave. An interval of 5 is a 5th, an interval of 4 is a 4th, and so on. Okay? Now, I wanted to go and just gently touch over some of our prefixes that we will be using. When we're talking about waves, particularly light, we're going to be using very big and very small numbers. So you will need to make sure that you know and memorize all of these prefixes. You're not just going to be using them in this class, so you'll be able to use them throughout your whole science career. Tera, symbolized by capital letter T, is 1 trillion, or 10 to the 12th. Giga, symbolized by capital G, is 1 billion, or 10 to the 9th. Mega, symbolized by capital M, is 1 million, or 10 to the 6th. Kilo, symbolized by lowercase k, is equal to 1,000, or 10 to the 3rd. Hecto, lowercase h, 100, or 10 to the 2nd. Deci is 10, or 10 to the 1st. It's symbolized by D. Centa, symbolized by lowercase c, is 1/100th, 10 to the negative 2nd. Milli, lowercase m, 1,000th, 10 to the negative 3rd. Micro, 1/1,000,000th, it's symbolized by mu, it's 10 to the negative 6th. N is for nano, 1/10000000th, 10 to the negative 9th. Pico, 1 trillionth, 10 to the negative 12th, symbolized by letter P. Now, we're going to use some of this information and our formulas to solve some problems. This first problem is very similar to a problem that you will find at the end of 11.1 section review and in the chapter 11 review. For this problem, we're finding the frequency when we're given a speed and a wavelength. Remember, whenever you have an equation, you can find the variables if you're just missing one. So we start with the formula that we use. V is equal to lambda f. We solve for frequency by dividing each side by lambda. We plug in our numbers, and then we get our solution of 115 hertz. The period of this wave utilizes the reciprocal relationship between period and frequency. Period is equal to 1 divided by frequency. How much more intense? Remember, I is equal to 1 over d squared, so 1 over 5 squared, 1 over 25 less intense. How much more intense is a 4 decibel sound than a 1 decibel sound? The distance between 4 and 1 is 3, so this would be 10 to the third, or 1,000 times more intense. We've covered those problems before. These next couple are going to be new. So, these next two problems use 8.4, particularly the italicized text, which is often just as important as the bold text. So middle C on the piano has a frequency of 262 hertz. What is the frequency of the fifth interval above middle C? Remember, an interval is the space between notes. So we're going to draw the scale and we're going to count 5 above C. We start at C with 1, and when we count to 5, we get to G. So G is the fifth interval. Now we look at the table on page 271 to find the ratio between C and G. That ratio is 2 to 3. We set up a proportion. It'll be the same for both sides. It was C to G, 2 to 3. C over G, 2 over 3. Okay? We then plug our value for C and find G by cross multiplying. So we take 262 over G is equal to 2 over 3. Cross multiplying it, 3 times 262 is equal to 2G. And then we just divide each side by 2 and we get 3 times 262 divided by 2 is equal to 393 hertz. The third overtone of middle C, that uses our ideal harmonic frequency is equal to the fundamental frequency times harmonic number. We're given our fundamental frequency of 262 hertz for middle C. So the third overtone, we just take 3 times 262 and get 786 hertz. Now, you should be noticing something interesting. To find the third overtone of C, we take 3 times 262. That number also appears in the ratio for C to G, 2 to 3. So the reason that a perfect fifth interval sounds great is because it helps hit and emphasize this third overtone. Okay? So the third overtone helps emphasize the note and make it sound better. Harmonic things that have consonants or good sounding harmony are going to have simple ratios like 2 to 3. Things that have dissonance are going to have really weird irregular ratios like 1.436 to 2.543, not simple whole numbers. To recap, simple whole number ratio is what causes consonance. And remember, both of these values depend on the frequency. So the frequency is what determines whether something is consonance or dissonance. Okay? Finally, we have this one over here. What is the speed of sound in air? We just take our formula of 331 plus 0.61 times the quantity T over 1 degree Celsius. We plug in our value for T, which is 40 degrees, and we get 355.4 meters per second. We only used 2 significant figures, so we round to 2 significant figures, and we get 360 meters per second. A couple of other things that I want to address are that flats and sharps reduce interval values. A flat or a sharp is going to change a full interval to a half interval. All right, guys? I know this has been a long video, but I hope this helped you with some of your problems. I've started to get some vocab cards in from you guys, and you are doing great. Just keep reading your book, going over the terms, and you're going to do well. Please, please, please message me if you want me to clarify any of this or go over anything more. I hope you guys are having a great Corona break, and I'll see you tomorrow.